Okay, so you have the privilege, whoever you are, of listening to John Louie's first ever podcast lecture. So I hope it's worth the time you've spent on YouTube here. We're going to do an interesting thing here today, I hope, and go through my 2001 paper, which basically was the explanation of the refraction microtremor technique. I will take you through that with a example data set, or maybe a couple of example data sets. First we'll open the paper, and I will go down to the methods section, and we'll take a look at what we need to do to record refraction microtremor data, and then as soon as we get to the equations, we'll start processing an example data set. So let's see. Basically, one of the reasons that refraction microtremor has turned out to be so popular is because it uses a type of data that's extremely common, and really, almost any department, almost any engineering company, almost any consultant is prepared to record these data. Essentially, we set out a very standard, and just because I'm recording video, you guys don't hesitate to ask questions, okay? Essentially, we take a very standard seismic refraction array. Commercially, it has to have at least 12 geophones. And we want that geophone array to be at least 8,200 meters long. So the kind of minimum setup that's available from Optim for with the software for $15,000, which is not a whole lot if you're starting up a consulting company. That's a 12-channel cable with 12 4.5 hertz geophones, and it's laid out. All right, hopefully we get a second file going here. So we have the minimum commercial setup is a 12-channel cable, 12 4.5 hertz geophones with a takeout interval on the cable of 8 meters. And so that gives you about a 100 meter array from geophone 1 to geophone 12. And that's the only other thing you need is digital recording of the data, which is a very something that's not difficult to arrange anymore, because we're going to be pulling out parts of the data that aren't obvious in the not the majority of energy of the data is not going to be exactly what we want to see. Okay. And then the rest of the methods section here talks about how to plant the geophones, the reasons for the relatively long geophone interval. 8 to 20 meters, I say there is best, and the reasons for the relatively low frequency geophones. We want to use as low a frequency as we can get, but if you go to say 1 hertz geophones, they tend to be very heavy. You have to dig dig holes and level them in the bottom of the holes, and that's too time consuming. So 4.5 Hertz geophones is a very good compromise. They're no more difficult really than any standard geophone. But we do. That's also why we level them. And any of you who have done or will do refraction microtremor work, you'll see that we do need to take, in addition to stomping the phone, putting the spike into the ground, we have to make sure that the geophone's approximately level. Now, another thing that's come out that I suggest here that really became prominent in our work in Las Vegas, collecting measurements. Okay, starting again. Refraction microtremor data is easily enhanced by a hammer source. And what that does is overcome some of the objections that a few people have had that we have a hard time tracing the surface wave dispersion curves at higher frequencies, and the hammer source provides those higher frequencies and allows us to get very stable velocity information out of the upper couple of meters. In general, with 4.5 Hertz geophones, and generally using the frequencies between, say, 1 Hertz and say 15 Hertz, as we'll see in the example data set, we can get good control on velocities from, say, 2 to 3 meters depth down to 50 to 100 meters depth in most places. So the need to get shallower velocities, both for the building code, which is it's really the main use of the refraction microtremor technique, and for the and for engineering design, foundation design, the main, those are the main motivations of doing refraction microtremor work. Not really seismic exploration, although we've done some application of it there. Not really subsurface structure, but really for civil engineering purposes. For that, we do want to get those shallower velocities and use those sledgehammer impacts. So all of that is really preparatory to on page 3 of or page 4 of the paper here. We begin the velocity spectral analysis, and so let's now load up a data set for an example. It'll be an example shot record, and let's go ahead and look at the details of that analysis. So I guess it's turning red just before. Okay, so to load up a data set, I'm going to start the JRG ViewMat tool. crack.seismo.unr.edu/JRG is where you can get all the software. The open source software does not include the actual ReMi analysis, but and here's a secret just for you guys, it includes the material that and the operations that I'm going to do here. So, commercial ReMi is developed as a process that combines several different well-known algorithms. One of the things we're doing in this class is we're exploring these well-known algorithms and learning about them. And so really what I'm going to take you through here is a demonstration of these well-known algorithms, specifically slant stacking, Fourier transforming to spectra. Those are two of the algorithms. They were published on 30 years ago. Even in combination, and it's really the combination of all those and the usage of them on microtremor data, not on shot data like we'll initially see here today. That's what's copyrighted, and that's the technology that is proprietary. And it's your privilege here as a student. You can actually work with this method and use it in your theses and in your classes, and you can look at the source code because you're working with us. So that's something unique. That's one of the things that's unique about our graduate program is the access to these proprietary methods. So I'm going to start up JRG with on my machine. I have it set up as I'll use the ViewMat 500 command, and all that is there are double clickable jar files that you can download that will start it up just as well. Okay, so I should probably lower the projector a little bit so that you can see the top menu bar. And so now, okay, I've lowered the projector so you can see the menu bar. And of course, on a Mac, depending on what, depending on which program you're in, the menu bar at the very top of the screen changes. So that's of course a Mac thing. And I have some preset data sets that I use in the Applied Geophysics course. So we're going to load a JRG pack, and that means we don't have to mess around a lot with plotting it correctly and all that. So that's down in the 453 class in the surf subdirectory, and let's see. So we want to look at Dixie Valley shot hole records numbers 106 and 114. And so, of course, you open up the GRG pack directory and just pick any of those in there. So you can't see the whole record, but that's okay. Let's see, maybe for I'll expand it a bit to 150%. Just so you can see it a little bit better. A key thing about records for ReMi analysis, and I explained this in the paper. You got to have at least 4 seconds of data. Why is that? In 706, you guys found out, if you took it, that where does resolution of different frequencies from each other come from? If you sample more finely in time, if you have a smaller delta T, do you get a smaller delta F? And the answer we found in 706 was no, strangely enough. The way you get a smaller delta F and better resolution of different frequencies is to have a longer total time recorded. And so if you want, the way it works out, and I take you through it in the paper, the way it works out is that if you want 1 Hertz resolution, then you need 4 seconds of data. Okay, so with 4 seconds of data, we're going to get 1 Hertz resolution, and that's what fortunately that's what we recorded in Dixie Valley in 1998. That was with that year's applied geophysics class. And here are two records. This is the record we're looking at, 106, is kind of an oddball. And if you've looked at a lot of seismic data, you'll know right away that why this is so oddball. You'll notice that the first arrival is pretty much simultaneous out at the larger offsets, which is in this case, the traces are 50 feet apart, 15.24 meters. So this is at 40. The 48th trace is basically 750 meters, actually 771 meters from the source, from the shot hole. And the refraction here is coming in simultaneously. How's that possible? In the presence of dip, and when the seismic waves, the refraction wave is traveling up dip, then it can be rotated to all hit the surface at the same time, and that's pretty much what's happening here. So that's a bizarre record. And how can we tell what's what? Well, the first arrival is the first arrival, so that's pretty simple. And that's direct P wave on the left, in the middle is the first refraction, and then the second refraction on the right side of the record. If we could see some hyperbolic things in here, we might think, well, we have some reflections. Awfully hard to see. Are these things that come after the first arrival but are parallel to it, are they reflections, or are they multiples coming off the, bouncing around in the alluvium between the bedrock and the surface? Hard to tell from here. There's a very, okay, then looking further at what the different velocities are in here, you can see the slowest thing is also the strongest. So if I plot the data, if I go edit clip at maximum, then the data is normalized to the maximum amplitude in the whole thing, and you can see the maximum amplitude is in this slowest wave, and that's actually a dispersive Rayleigh wave. And the refractions are very low in amplitude. So, most of the energy coming from the shot is effectively trapped between, in the upper part of the alluvium and traveling as this Rayleigh wave. And how do we know it's a Rayleigh wave and not a Love wave? Well, these are recordings from vertical geophones. So that's the Rayleigh wave is the one in, at least in normal conditions, that's going to have some vertical component of ground motion. In between, something else. Okay, also very slow, but not as slow as the Rayleigh wave. Candidates, maybe a higher mode surface wave, or perhaps just maybe this is an S wave refraction, or let's say this is an direct S. And then here would be an S wave refraction. It should be at somewhere around twice the travel time of the first arrivals, and that's sort of what it appears to be. Again, I'll go back. I'll go back to plotting it, clip at RMS, just to show those smaller waves better. Yeah, so maybe some of this low frequency stuff are shear waves, shear wave refractions, shear wave direct waves. One thing I teach in applied geophysics is, how do you figure out, which waves are which? And one thing you always want to check is for the air wave. The air wave should be traveling at pretty close to 330 meters per second, and that's part of the exercise that the class gets here. And that's pretty much following the Rayleigh wave in this data set. So here my feeling is the air wave, which ought to be high frequency, but straight, like the surface wave, the air wave is following it's kind of buried beneath the surface wave. Okay, now the surface wave is much more kind of normal, if you like, in the second record here, which is record number 114. Here you see basically a very straight first arrival refraction, okay, and lots of multiples of that. You see some signs of reflections. You know, these have a little bit of that normal move out that you want to see. This was a reflection survey after all. You're still seeing the same, you know, possibly S-wave refractions in between, and then this relatively slow Rayleigh wave, and somewhere below it is the air wave. All right, so that brings up the issue. You know, how are we and you know, the students in applied geophysics ask me this all the time. How do we tell which wave is what? Well, we're looking at the velocity. We're looking at the slope. Okay. So we have just been looking at the theory of a method that separates waves in a record like this based on slope, the slant stack. Okay. So let's go back to the reprint, and so here maybe I should enlarge it even more. You know, here we have the continuous equation for the slant stack, and so you can see that to get the slant stack signal at one value of p and one value of tau, one p-tau pair, so that's one pixel on your p-tau plot, on your p-tau image. That's this integral, okay? And it's a line integral. It's a line integral across x, okay? And you know, it goes in steps dx. And it's basically taking a slanted path, so it's taking the value of the scalar field A, which is the data here. So you know, here's A, and X is across the top, and so maybe I should relabel that by looking at the plot parameters. Okay, so I'm going to relabel the vector interval to 15.24 meters, which is 50 feet. And instead of being trace sequence, it's going to be x in meters. Okay, we've already got the time axis labeled okay. Time in seconds, so that's all right. Apply changes, that just changes the axes. So now you can see at the very top, maybe you can see x in meters from 0 to 731. Now this x is not strictly the offset; it's just the x-axis. This particular record, it actually. Okay, so in this particular record, you know, x actually is the offset, but if you if we go back to the other record, you'll notice that the source has to be off the left side of the screen, left side of the plot somewhere, and so I think you have to take the x and add 40 meters, and that'll give you the actual offset for that record. But in our analysis, this isn't going to matter. We have some sort of x-axis. Okay, so we got x and t. T goes from 0 to 4 seconds. X goes from 0 to about 732 meters. Okay, and so the slant stack is going to trace you know, this radon transform generally and what is A? All right, I can see the values of A if I make some picks on this. Okay, so if I pick right in the middle of the white, you can see in the pick window I'm getting some negative values there. If I pick on the black, I'm getting positive values. So that's, and that's a scalar value. That's a scalar field. Okay. A could be complex. That I still consider that a scalar. Here we have, a real scalar field. In the noise, before the first arrival, the values are much less. All right. Up in the surface waves, despite being, saturated on the plot, the real values are still there. Up at 1400, 1500 instead of a few hundred like they are in the refraction. These reflections down here, they're getting up to a couple hundred in amplitude. So that's the scalar field A, and we know, of course, we see its waviness. It's going positive and negative. We see its waviness, and that's the kind of field that we're going to slant stack today. We could slant stack images. We could slant stack fields that are all positive. Like we can take a slant stack through a slowness field, which is all positive, and that's actually tomography, as we'll learn. But today we're going to take a slant stack of a wave field. Okay, so we're at a certain, let's say we're looking at tau, which is, say, 1 second is about here. We want to slant stack from tau, and we want to slant stack at, let's say p equals 0. Slowness of 0. That's a flat line. Okay, so what we would be doing is starting at p equals 0. We'd start at p equals 0, which is over here on the left. We start at tau equals 1 second. And then we would follow for p equals 0. We would look for times equal to tau plus px. Okay, so tau is 1 second, p is 0, so it's going to be the same on all the traces, and we would be basically adding up, integrating across this line, which is p equals 0 and at tau equals 1 second. All right. So, and if p was say 0.5 seconds per meter, that's probably too slow. If p was 1,000th of a second per meter, then by the time you got you start at p equals 1, say, and by the time you got to 730 meters, you'd be at 730 milliseconds plus, added on to the tau of 1, so you'd be down here. So that would be, from tau equals 1 down, across a slanted line. Okay, and you can see that tau of 1 millisecond per meter is, kind of close. It's in the range of a lot of the slopes in this data set. Okay. Now here is the, down below in the paper, equation 2, that's the slant stack expressed in discrete form. Okay, so we got the continuous form with the integral, we got the discrete form with the summation. All right, and that's actually how we would do the slant stack in how you do the slant stack in the computer, and how this is exactly the summation equation used in the slant stack code that I'm going to show you the operation of here. So instead of being at p, we're at some minimum. Well, we're at p. That's the continuous value that we want to be at. Let's say it's 1 second, and that's going to be at some minimum slope, p0, and sometimes we set p0 to be, say, 0. And then times, or plus, an interval in p, right? We got to discretize our slant stack you know, in steps of p and steps of tau, just like we have our data discretized. Right. So the question is, you know, what is L? So this is the continuous p is equal to some p0, okay, which is an integer L. You know, we're looking at the first p sample, the second p sample, the 2 millionth p sample. Okay, that's L, and then times the interval in slowness in p.
So in each of these cases, J, I, K, and L are your discrete steps.
That's exactly right. Those are the indices. Okay. You know, if we go back to the data and the picks, okay, there is the time index. So that would be I, right? That would be I, and I times dt is equal to t, and there is the time in seconds.
It's different for each of your locations, for each of your discrete locations that you.
Right, because each of these picks that I made is at a different x and it's at a different time. Okay, so so this one is at I equals 724, which is 724 milliseconds, and the one I made before that, wherever that is at I equals 360, which is 360 milliseconds. And then here's the index of the I think that's there. Here's the index of the in x, right? Which trace is this? That's and the first trace, the leftmost trace is the 24th. Oh, that battery's bad too. And then here's the distance. So that's 24 is j, and dx is 15.24 meters, and there's x in meters. Okay, and that's j. It's the the 24th trace, if you like. So that's how the discretization works. Okay, so we're gonna see the same. We'll see how long this battery lasts. We're gonna see the same thing when we go to when we're looking at the p-tau transform. So we're gonna take this picture on the left, and we're going to transform it to p-tau with this. Here's the continuous transform with the integral, and there's the discrete one with the summation, and we're just going to produce another picture, which is the transform picture. Okay, the slant-stacked section. All right, and so it goes. X is equal to j times dx, and t is equal to I times dt, and that's equal to tau plus px. There's that continuous equation. Here, the index for tau is k. One little wrinkle here: the dt tau is sampled the same way that t is. I don't change that. I mean, that would just be too confusing. But definitely, we have to have a different dp than we have dx, because those are just totally different fields. Now, this also tells you one thing that I'm doing with these slant stacks is I'm sampling. This is integer L times some constant dp, interval in slowness. That means I'm sampling linearly in slowness, which means I'm not sampling linearly in velocity. It's an inverse sampling in velocity, really. Okay, so that's a little wrinkle there. Okay. So all right, here's the equation we're gonna do before the battery runs out. So I can go down to on each plane, and I have yeah, it's called slant planes that will individually slant stack the two planes. And then here's all the this is the minimum tau that I want to consider. There's the dt, okay, and that's 1 millisecond. That's correct. So in JRG here, you get these little dialogues that come up for any particular method, and you've got to enter all the different, or at least check and make sure you've got all the right parameters for your transform. And that's basically what's set, in the summation equation down here. All right, so now it wants to know the x of the first of the trace on the left, and that's 0. It wants to know the dx, okay, and so that's the same dx as here, and that's 15.24 meters. And it wants to know what my tau 0 is, and notice that this equation assumes that that's 0. So that's interesting. I didn't allow to start it at any non-zero tau. Okay, but there should be a tau 0 there. And let's see. Now P0. It wants to know what P0 is. All right. So for now, we'll start with a P0 of 0. Okay, and it wants to know what dp is. Okay, what is the interval in this? And it's put in some guess, and I forget what that guess is based on. But let's figure out what we want in terms of seconds per meter. Yeah, it's put in a very small number. Okay, so let's see. This depends on what we want to be our minimum. What is the minimum velocity we want to consider, right? No, that's not it. What's the minimum velocity resolution that we want? Okay. Well, and it's nonlinear in velocity, so we need to find a sampling of. We need to find a sampling of slowness. Okay, so if I 0p is going to be flat. Okay, and then we already figured 1,000.001 is going to be slanting like that. And I want a little more resolution than that. That's pretty steep already. So maybe I better take 10% of that. So 1e minus 4. Oops. 1/10,000th will give me a slope of like that, and then I can go up from there. Maybe I need less than that. 1e minus 5. Okay. And then n tau is telling me how many total, how much time am I going to include? Okay. So that's just saying, 4,000 times 1 millisecond sample interval in time means we're going to do all 4 seconds. So that's fine. We can explore that. And then here's the question: how many P samples do I want? And remember, I said that we ought to have the same number of traces in slowness as we have traces in X. And so that's why this is set to 48, because we have 48 traces in X. And by information theory, if we get the right range of slowness, we ought to have almost everything, in 48 traces of slowness. Okay, so okay, that's where I'll set that, and then I say slant planes. Okay, what have I found here? I've probably noticed that these that's the slowness is increasing across the top from 0 to 4.8 to e minus 4 to 10 to the times 10 to the minus 4. We've got 4 seconds still of intercept time at the bottom. Okay, but these traces are not changing very much. You can see a lot of lines through here. But there's not a lot of difference. What if I plot it? If I clip it maximum, there's some things coming out. But you know what? I kind of undersampled on. I'm not getting up to a high enough slowness to really see much. It's like the strip is too narrow, and it's kind of oversampled. So we'll just cancel that and do it again. Okay, and so I think we'll continue on Monday, and but we've almost got the slant stack wired here. So I tried 1e minus 5. I'll try 1e minus 4 this time. Oops, minus 4. Okay. Slant planes. Okay, now we're seeing some more features. All right, so on Monday I'll start out talking about this.